Hello, thank you very much for attending. This is a wonderful conference. I'm based in Taiwan at the moment, and maybe you know there's some cooperation between Lithuania and Taiwan. So my German name has become a bit shorter. Now it's Se Ole, and I work at Tsinghua University in Taiwan. What I want to talk about today is um, you probably are familiar with the Wigner distribution, which is wonderful to represent quantum states because it's real valued, but it's not so well appreciated that the dynamics can be studied in terms of the Wigner distribution as well. And in that case, you end up with a very intuitive picture, which I want to describe to you. So here's a one-page summary of my talk. I want to introduce to you this vector field, which describes the movement of the Wigner distribution in phase space. For those of you who are not so familiar with the Wigner distribution, it can have negative values, which sometimes are referred to as negative probabilities, and these are clear signatures of the quantumness of the state. And what you see here in this double panel is I talk about a beam splitter with zero reflectivity, a 50-50, or 79 versus 31 or whatever it is probability. So I'm basically talking about a variable beam splitter mixing the modes. And then if you change the beam splitter reflectivity, you can pretend it's like a time, and time then can be described dynamically. So the outline of my talk is I want to briefly remind you of the connection between Schrödinger von Neumann and the Wigner distribution dynamics. I will emphasize a little bit non-classical aspects of the movement of the distribution phase space, and then I will give you some examples like the beam splitter example just now. Oh, and lots of pictures. So the quantum state is in general described by a density matrix. You plug the density matrix according to the Schrödinger von Neumann technology into the commutator with the Hamiltonian, and that way you get the time evolution. I emphasize here that the operator product is, of course, a non-commutative product. Well, because the operators are non-commutative, we typically say. So the question, maybe some of you know the answer, but the question is in general, how does this map to phase space? Because the Wigner distribution is a real valued distribution. So you take an operator, then bracket it to get a function, then do this Wigner Fourier transform, which he explained, presented in his 1932 paper, and you end up with a Wigner mapped operator to a phase-space distribution. So now you have a function, the Wigner mapped function operator becomes a function of x and p. So how then does the operator product, the non-commutativity, map over? A specific example is if you take the Wigner, if you take the density matrix, you get the Wigner distribution. But in general, if you now Wigner map the evolution equation, then you should get some new evolution equation. And you see in this evolution equation, you have the symbol star, and star stands for the Grunewald star product. So historically, in 32, Wigner presented the Wigner distribution and the evolution equation. Then José Moyal worked out this version with a sine function with these operators, and independently, Grunewald in Holland worked out the star product, which gives rise to the sine function. So effectively now, what happens is that I wanted to show some other animation, whatever. So maybe I'll go back. So the operator product of quantum physics gets mapped to the star product in phase space. In my talk, I want to emphasize that this can be rewritten. You can pull out some derivatives, and you can always form a gradient, a divergence operator. And so you can rewrite this as a vector divergence. And so you end up with the time derivative is equal to the divergence of this vector field. So you have a continuity equation. And specifically, I'm interested in the shape of the vector. So here's my wonderful animation. So the star product, the operator product gets mapped to the star product. And you can also write the von Neumann equation now as a continuity equation. Moreover, it gives rise to a vector field, which allows you to visualize the dynamics in phase space very well. Have I only talked for 5 minutes? That's great. So here's an example. Um, when I started to investigate this, I kind of couldn't believe it. So here you see the vector field I just showed in the second transparency, but now I line integrate the vector field lines just in order to get a better view of what is going on in detail. So specifically here, inspired by classical physics, I was looking at the stagnation points, where the current of this transport is zero. But whereas in classical physics, the current can only be zero at zero momentum, because if the momentum is non-zero, then things are moving. In quantum phase space, because the Wigner distribution has this peculiar feature that it can have negativities, you can have non-zero points popping up somewhere else in phase space. So this last sheet is actually a sheet that displays the phase space. So you see it's x and p axis. And here the rainbow colors give you the time development. And I only wanted to highlight in this particular graph the evolution or the movement of the 0 points, the stagnation points of the current of the dynamics as a function of time. This specifically is a two well tunneling case. So you see a stagnation point in one well and the other well, and then some complicated stuff in the middle. Note this little ring. This little ring is a representation of the fact that the stagnation points underlie some topological protection, because the current field around the ring can't be discontinuously changed, and therefore is topologically protected. You find more details in the paper I mention here. So I've told you a little bit about the visual appeal of the Wigner distribution study in phase space, a bit more of the technical details on how this differs from classical physics. So for example, we call typically we call the quantum, I call the Wigner continuity equation. I'm the only person in the world who calls it that. Everybody else calls it the quantum Liouville equation. Liouvillean physics, of course, is tied to the volume conservation in classical phase space, giving rise to chaos in high-dimensional systems and all that. And in quantum physics, we don't have that. The volumes can change. In fact, they can change catastrophically. So I call it confusingly the quantum Liouville equation, because phase space volumes actually can change in a singular fashion. Finite phase space volumes can disappear infinitely quickly or pop out of nowhere. When you think that through a little bit, it's actually quite intuitive. The Wigner distribution has to be able to develop negativities, and this is catastrophic change. So it's not just a dilution or contraction phase space, it changes sign, and that implies that the phase space volumes have to be able to singularly change. Because of that, you also typically do not get trajectories in phase space. This unfortunately has led to a lot of confusion in the chemical physics or physical chemistry community, because they try to model dynamics of the Wigner distribution using classical fluid dynamics approaches. And so this is not possible because volumes change infinitely quickly. So with the help of my students, I wrote some opinion piece on this. And perhaps when I just slagged off the chemical physics or physical chemistry community, then perhaps we should forgive them. José Moyal, who this double bracket is named after, was stopped by someone with the name of Dirac. I don't know, I've just heard this name, Dirac. There's a medal named after him. Some dude from England. He stopped Moyal from publishing his paper, I think, for 7 years or something, several years, because Dirac said, you're talking, how do you say bullshit in French? Or whatever. He said, you don't understand physics, you're talking nonsense. There are no trajectories in phase space because of Heisenberg's uncertainty principle. Phase space is fuzzy. So yeah, Dirac got that wrong. And it's not the uncertainty principle that's behind it. Should I expand on this? Maybe just one little statement. You're all familiar with the harmonic oscillator. The harmonic oscillator is a stiff rotation in phase space. Literally, you can draw your Wigner distribution somewhere, put a pin in the center and just rotate it around. So there are obviously trajectories, totally clearly. There are trajectories in the case of the harmonic oscillator. So many people think there are no trajectories because of the uncertainty principle. Not true. The uncertainty principle shapes the shape of the wave function, but the dynamics in the case of the harmonic oscillator or such simple potentials can actually be classical, as in it has trajectories, but typically it does not. So one example where it does not is, for example, a beam splitter. Let me pretend that I'm a gangster from Hong Kong and I have 100 different sunglasses, with very little reflectivity, 20% reflectivity, 50, 80, 90. So I scan through all these reflectivities. I can do that with an effective Mach-Sehnen interferometer where I change this phase. So now I have a variable beam splitter. I mean, that's how you would probably make it in the experiment. And with a variable beam splitter, I can map to a variable reflectivity and transmittivity. I can pretend that this is a Hamiltonian because eventually it is. And so then I can map the change in reflectivity to a fictitious time. And with that approach, I can now unfold the Wigner machinery and create the time evolution for this case. And then I have to trace out the other mode because here I'm implicitly talking about a two-mode system. I come back to a transparency number 2. And then you end up with some kind of effective this is the Moyal bracket I have to trace, and then I get the Grunewald product, and I end up with a Wigner current. And the current in this case for mode B, for example, has this simple form. So it is the Wigner distribution for 2 modes, then multiplied with the other mode's momentum or position, and then I trace, and then I get the Wigner current on this side. So the A mode is being traced out. And the same is true for the B mode. And then they look almost the same except for a sign change. And now it's time for some pictures. So I already showed you this one. So here, for example, this is what it looks like if you mix 2 off-kilter squeeze states, and then you all know from optics intuition, the squeeze states, of course, when they mix together at 50-50 beam splitters, they become more mixed, so the distribution becomes wider. But here you can actually see the details of how this is being transported in phase space. This other example I just gave a moment ago, so the 3-photon Fock state and the coherent state as initial states, 50-50 mix, then unmixed again by going through a beam splitter that's even more reflecting. Even more reflecting, you see the states are being mapped over. Coherent now ends up here and the Fock over there. And here the famous, well-studied Hong-U Mandel experiment, but with a new little twist. So you put in 2 Fock states of single photon Fock states. And then what you see is, because the Wigner distribution has zeros, the velocity field develops singularities. So this is one manifestation of this singular volume change. So a striking departure from classical physics, where we do not really have infinite velocity fields, which is why the physical chemists struggle so much. They ended up with infinite velocities in their code and concluded the Wigner method doesn't work. That's actually not true. There are modern techniques to do this, which even interestingly have a Schrödinger form. So it seems fairly efficient way of modeling Wigner dynamics. Here, one last example. At the lab where I work in Taiwan, we use some squeezing experiment. So this is the squeezing current. And then of course, that this gives rise to this, these are our experimental data. And the emphasis here is that we found very interesting. The squeezing itself is well understood, but the coupling to the environment, what I wanted to show you is, so the squeezing is well understood, but the coupling to the environment, which is described by the Lindblad form of the coupling, look at how beautifully simple it looks in the Wigner language. It is a classical current that travels friction towards the origin, but then you have to preserve the uncertainty principle, otherwise you end up with a delta function. So you have a dissipative term, which is of diffusion type. So it's actually a diffusive term that preserves the uncertainty principle. And with that, I want to thank you very much.
Thank you. Questions?
So thank you very much for the very interesting talk. And so in your talk, you mainly focused on the Gaussian dynamics, such as the beam splitting operation or the squeezing. But is it also possible to do some non-Gaussian, like the analysis of non-Gaussian processes and like do some classical simulations of how these complicated the dynamics should look like or something like that?
Yeah, so the answer is no. For example, here, this is non-Gaussian, because actually the other part of the Wigner distribution affects how this side of the Wigner distribution evolves. So, I'm warning myself. So in other words, yes, in the chemical physics community, they have very nonlinear potentials. And there it was actually specifically invoked, this technology, in order to use nonlinear potentials. And then they made some mistakes. So yes, let me phrase it differently. I showed you that this is a mapping of the von Neumann equation, right? It's just a Fourier transform of the von Neumann equation. So I always say, you take von Neumann, you Fourier transform, you're with Wigner. You don't like Wigner, you Fourier transform back. It's totally equivalent. Sorry, that was the short answer. It's totally equivalent. It's a Fourier transform, a fast Fourier transform if you want.
Due to the time limit, let's thank the speaker again and move on to the next.